Hello again. So we'll continue with our lectures on the heart, and today we're going to focus on the cardiac muscle contraction and electrical activity. So you should remember from your first A&P course about how skeletal muscle contracts, and we've talked about the generation of an action potential, and we talked about depolarization and repolarization and hyperpolarization. So you might want to go back and review that because this is based on that. So I'm assuming, which is probably a bad thing to do, assuming that you remember a lot of that. So I'm going to say some things that remember when. So if you don't, you need to go back and look at that. So cardiac muscle contraction is a depolarization of the heart that is rhythmic and spontaneous. Okay, so this is involuntary. There's no nervous central control that's going, okay, beat, okay, beat, okay, beat, like there is with skeletal muscle contraction. And that is, it occurs because about 1% of the heart cells are actually automatic. They have what's called automaticity. And so they're self-excitable. They don't need a central nervous system impulse to cause them to respond. They will respond on their own. They will generate their own potential, their own action potential, and cause the heart to beat. Remember when we talked about desmosomes and gap junctions? The gap junctions between these cardiac muscle cells is one of the ways that allows all that electricity to spread through the heart and allow it to beat as a unit. Okay? The heart also has what's known as a long refractory period, which doesn't seem long, but 250 milliseconds is long enough to allow the heart to relax and the ventricles to refill with blood. So it won't just it won't beat and beat and beat and not give the heart a chance to at least fill back up with blood. So this hopefully looks a little bit familiar from your skeletal muscle. So we're going to take what we learned in skeletal muscle and think about how that would relate to cardiac muscle. So remember, cardiac muscle looks very similar. It's striated, it has the sarcomeres, but it's highly branched. And you have those desmosomes that keep the cardiac muscles from separating, and the gap junctions, which allow for the flow of ions through the muscles quickly so that the heart can beat as a unit. All right, and so the first step is depolarization. Just like remember if you think back to skeletal muscle, we had depolarization, we had repolarization, and then we had something called hyperpolarization, if you remember that. And the depolarization in skeletal muscle was due to the influx of sodium ions, okay? The repolarization was due to the efflux, or the going out of, potassium ions. And then remember, those potassium channels stayed open just a little bit too long, so a little extra potassium left and kept the muscle from contracting. So that kind of put it in a refractive period so that the muscle wouldn't contract. So it's similar in the cardiac muscle. You have depolarization. It's very rapid. So rapid influx of sodium through voltage-gated sodium channels. If you don't remember the difference between ligand-gated and voltage-gated, you may want to go back and look at that. So these are fast-acting voltage-gated sodium channels. And so you get a very positive feedback. As soon as they open, more and more and more and more open and allow more and more and more sodium. So it's a very rapid depolarization. Okay? Once it reaches the plateau, you get a change or an opening of calcium channels. So you don't see that in skeletal muscle during an action potential. But during action potential in the cardiac muscle, you see influx of calcium. And these are slow channels, but they allow a slow amount of calcium to continue to inflow into the heart because the potassium channels haven't opened up yet. So you've got a little bit of calcium influxing, keeping this plateau phase, keeping it toward the positive end of the action potential. So if you're looking at membrane potential, it's more positive. As the potassium channels begin to open, all right, these calcium channels start to close, potassium channels start to open, and you get a fast repolarization. Okay, so the difference between a skeletal muscle and a cardiac muscle is that that plateau phase with the calcium. And we've got our tension overlaid, so you can see when the actual contraction occurs relative to the action potential. And you expect it to occur just slightly after the action potential. So you've got the depolarization, the muscle starts to contract, and as the depolarization is occurring, then the muscle will relax. Okay? And the way this works is the heart has its own intrinsic conduction system. So it's got its own set of electrical wires, if you want to put it that way. So it's called the intrinsic cardiac conduction system. And these are a network of cells that don't contract, these autorhythmic cells, okay, that will initiate and distribute that action potential, that depolarization and contraction throughout the heart. So again, you don't have to have the nervous system initiating these responses. You have cells that will do that, initiate their own response, and then that will spread through a separate set of electrical conduction system in the heart. Okay, so this is separate from how we've been thinking about nerves, central nervous system, peripheral nervous system, nerve. This is separate. It's like the heart has its own electrical system. Okay. So this is what this intrinsic conduction looks like. You have what's called a SA node or sinoatrial node, and this is called the pacemaker. It generates the impulse. So this is that autorhythmic portion of the heart. It will generate those impulses and initiate the contraction of the heart. Well, if you haven't studied your anatomy of your heart too well, remember the heart, you know how I always I draw it like this a lot as a cross? These lines represent septum, and you have there's an internal scaffolding in the heart that gives it its shape. You have an atrial ventricular septum, so basically a wall that separates the atria from the ventricle, and then you have a wall that separates the two ventricles and the two atria. So you have this wall here. And so this particular wall here, this is the atrioventricular septum. So if you haven't looked at your anatomy, go back and look at your walls. The septum that separates the atria and the ventricle, the one that separates the two atria, and then the one that separates the two ventricles. Well, the one that separates the two atria is pretty thin, and it doesn't really impede the electricity, okay? So that sinoatrial node, once it starts to generate those impulses, those electrical waves, because you have those gap junctions in cardiac muscle tissue, will spread readily through both atria. So they just rapidly spread through both the atria, causing them to depolarize. That's the impulse that's going to cause depolarization of those cardiac muscle cells for them to contract. Well, the septum between the atria and the ventricle, it's really thick, and it won't allow that electricity to go through. And so you've got to regenerate it. So you've got to have basically something carrying that electricity across that septum. And so we have what's called the AV node. So when the SA node generates an impulse, it will travel to the AV node, and the AV node will pause just briefly, right? And that allows the atria to contract before the ventricles. The atria will depolarize, contract, and repolarize just slightly before the ventricles. Because remember, you want the atria to contract and push that blood remaining down into the ventricles. Then the ventricles need to contract. You don't want all four contracting at the same time. So the two atria will contract, then the two ventricles will contract. All right, so you have that AV node, pauses it just a second, just 0.1 seconds. And then that electrical impulse will then travel down the septum, okay? And this is called the AV bundle, or atrioventricular bundle. That bundle will then split into bundle branches, and one's for the left side, one's for the right side. So you'll have your right bundle branch feeding the right ventricle, and you'll have the left bundle branch feeding the left ventricle. And this is like a nerve, and so it's going to then branch out into what are called Purkinje fibers, and so it's going to innervate all the cardiac muscle cells in the heart. All right, so these bundle branches split, and you get these Purkinje fibers, and they're going to cause the depolarization of the cardiac muscle cells as a whole unit. So now all of these cardiac muscle cells will contract at the same time. Okay, so that's what it looks like. That's the intrinsic conduction system. You have your SA node, your AV node, your AV bundle, your bundle branches, and your Purkinje fibers. All right. So in order for that SA node to work, it has to have its own, we call it the pacemaker. It has what's called a pacemaker potential. And so this particular way that it functions allows it to automatically generate an action potential over and over and over again without an external source. So without the central nervous system sending an action potential down to cause it to depolarize, it will just depolarize on its own. And that's because it has this pacemaker potential, which is because you have this very slow depolarization because you've got sodium channels opening and potassium channels closing at the same time. just a few more sodiums than potassium, so you get this slight depolarization. All right, so once it hits that threshold, we talked about threshold before, then it will fully depolarize. All right, but this time, unlike skeletal muscle and even cardiac muscle, in these pacemaker cells, like in the SA node and the AV node, you get depolarization because of calcium. So calcium channels open, and that causes the action potential, causes the depolarization due to the influx of calcium. And then just like in the other cells, you're going to repolarize. The calcium channels are going to close. Potassium channels will open. Potassium will leave the cell and cause the cell to repolarize. But instead of getting that hyperpolarization like you're used to, those sodium channels will start to open and quickly start it going right back up. So that pacemaker potential will kick in before you get any hyperpolarization and start that pathway to repolarization again. So that's called a pacemaker potential. All right? So again, so the sequence of excitation, the first thing that's going to depolarize is going to be the SA node, or your pacemaker, and it's going to generate an impulse about 75 times a minute. And we call that sinus rhythm. So a normal heartbeat, if your SA node is in charge, which is normal, should be about 75 beats a minute. Now, when you slow down a heart or speed up a heart, that has to do with your central nervous system. If you think back to your sympathetic nervous system and your parasympathetic nervous system, that's when your nervous system kind of takes over and helps control what the SA node does. But in just times of rest, that SA node will just beat every 75 beats a minute. And it depolarizes faster than any other part of the myocardium, so then that potential will spread through the atrium. Okay, so it spreads to the atria, and then it gets the AV node. There's a slight pause. Okay, there's just a couple of fewer gap junctions, causes a little bit of a pause because you want the atria to have time to depolarize and contract. Now you're going to send, once the atria contract, now you want the ventricle to contract. It will now send that signal to the AV bundle. Now, if something was to happen and your SA node no longer worked, you would still get a heartbeat, because the AV node will actually beat on its own. It will depolarize on its own 50 times a minute. Okay, so for some reason your SA node, there's some kind of blockage, and so now your SA node is not allowed, you can't get that impulse to your AV node. Your heart will still beat. Your atria may not beat. Okay, so you'll just have passive flowing of blood from your atria into your ventricles. You won't get that contraction, but the ventricle will contract and pump blood to your body. Okay, so that's okay. You should still stay alive. All right, so if your SA node doesn't beat, your AV node will beat, but it's at only 50 times a minute, so you'll probably not feel real good. You'll be pretty tired. So that impulse then travels to the AV bundle, which is also called the bundle of His, and then from the bundle to the right and left bundle branches, and then out to the Purkinje fibers. All right, and so one thing I wanted to say, this AV bundle, remember, that's the only electrical connection between the atria and the ventricle, because you have that really dense septum between the atria and the ventricle. So you've got to have that bundle to carry that impulse from the AV node into the bundle and cross that septum. All right? So what happens, what if something goes wrong with this electrical conduction system? If there's some deficit, you can get arrhythmias, which are just irregular heart rhythms. So you may have heard of someone with some kind of fibrillation, or atrial fibrillation, or ventricular fibrillation, or some kind of heart. They need a pacemaker. Maybe their sinoatrial node's not working anymore, so they put in an external pacemaker. And if the system's not working in a coordinated fashion, you can get uncoordinated atrial and ventricular contractions. So instead of going thump, 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 it's like dun, 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 dun. I mean, it's just kind of beating all over the place. So it doesn't pump very effectively. So that can happen. You can get fibrillation. You can get rapid and irregular contractions, and they're just useless for pumping. I'll try to find a video, but again, I always tell you guys this in case I can't find one, or look one up in case I forget to post it. But look up fibrillation. You can actually see videos of atrial fibrillation and ventricular fibrillation, and it looks like the heart's a little bag of worms. And so you can tell just by looking at it, that's not very effective. You can live with atrial fibrillation. People are in AFib. Even though the atria are kind of jiggling like that, the blood will still leave the atria into the ventricles. And then if the ventricles are working, it's fine. But ventricular fibrillation, when they're just kind of wiggling like that, you don't get a good heartbeat, and that's you're going to die. So Atrial fibrillation you can live with. Ventricular fibrillation, you need to be put on a, you know that thing that they put, what do you call that thing? You know, clear, you know, the paddles. I'm totally at a loss for words. We'll think of it later. You know what I'm talking about. On TV when they put the things on your chest and shock you into rhythm. Yes, they shock you into rhythm. So that's what happens when you have ventricular fibrillation. All right. If you have a defective, it's late in the day, guys. I bet you can tell that. Defective SA node. You can have what's called an ectopic focus. So if that SA node is defective, the AV node will take over. That means so a different place, another pacemaker is taking over. So again, you'll have a heart rate that's much lower than that 75 beats a minute. But you can still be alive because your ventricles will still beat. Now, if your AV node is defective, that can result in total heart block and death. Okay, because the AV node, if it's blocked, then that conduction can't cross the septum and get to the bundles. All right, if it can't get there, you can't depolarize the ventricles won't contract, and you can die. All right, so I'm going to stop here. I'm going to do this one in a separate video. I think EKGs, I want to spend a little more time with that, so I'm just going to break this talk into two. All right, thank you. See you in a minute.